Hello, everyone. Welcome. I'm Jet Aguilar from the Astronomical League of the Philippines, and I will be hosting today's webinar. Thank you so much for joining us for our 2023 Astronomy Expert Speaker Series online lecture series. And I'm also very happy to welcome our esteemed speaker for today, a Jesuit brother and an astronomer from none other than the Vatican Observatory, Brother Robert J. Macke. He will be talking about meteorites in the Vatican. The Vatican, the Vatican Observatory is an active scientific research institution with roots dating back to the 16th century and houses a collection of more than 1,200 meteorite specimens at Castel Gandolfo in Italy. Brother Macke will discuss the research he is conducting on meteorites, physical properties like density, porosity, magnetic susceptibility, and thermal properties. He will also touch on the application of his work to NASA's OSIRIS-REx space mission and the samples from asteroid 101955 Bennu that the spacecraft will deliver to Earth this September. My fellow ALP member, Mr. Edwin Aguirre, will be doing the introductions for our esteemed speaker later. For those who are not able to register but would still want to watch this ongoing webinar, we are currently live streaming on Facebook at the Facebook page of the Philippine Astronomy Forum. And before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms, preferably the complete names, to help us facilitate this process in sending you your certificates of attendance. Enjoy the webinar and let us all have fun learning. Here's the program flow for today's webinar. And now I would like to turn you over to Mr. James Kevin T., the President of the Astronomical League of the Philippines, to give his welcome remarks.
Thank you, Dr. Jet Aguilar. Good evening to our viewers in the Philippines, and good morning to our guests in the United States and Europe. My name is James Kevin T., President of the Astronomical League of the Philippines. On behalf of the ALP, I would like to welcome you to our Astronomy Experts Speaker Series 2023. This webinar is part of the ALP's International Astronomy Educational Outreach Program. Our goal is to bring renowned experts and scientists to the Filipino people and to the rest of the world. That's the reason why the webinar is being offered free to the general public. I would like to take this opportunity to thank ALP members who have been instrumental in putting this program all together. I'd like to thank especially Imelda Johnson, Edwin Aguirre, Dr. Jet Aguilar, Jun Lau, Kendrick Cole KCT, Andrew Ainchan, and Peter Benedict Tubalinar. So this is the 15th lecture in our speaker series. Our speaker for today is no other than Brother Robert Macke, SJ, a research scientist and a curator of meteorites at the Vatican Observatory. We have more distinguished speakers lined up for the coming months, so please try to tune in, and please do not forget to register in advance for these future webinars. Thank you very much. And by the way, I would like to also to invite everyone for tomorrow's ALP has a special free public telescope viewing at SM by the Bay at SM Mall of Asia. We will be celebrating the International Solstice Festival, which coincide also with the International Sunday Solar Event. And in the evening, we also coincide with also observing into the moon, which is also a part of the program of the International Observe the Moon Night. No? So the event will start at 3 o'clock in the afternoon up to 6 o'clock for the solar viewing. No? So this get to give you a chance to observe the sun in a white light and hydrogen alpha. And in the evening at 6 p.m. to 9 p.m., we'll have the moon observation as well as night observing of the celestial objects. No? So with further ado, I'd like to turn over the event program to Imelda Johnson, to Edwin Aguirre, who will introduce our guest speaker for today.
Thank you very much, James. And it is my distinct pleasure to introduce to you our guest speaker for today, Brother Robert Macke, S.J. As Jet and James had mentioned, Brother Macke is a research scientist and curator of meteorites at the Vatican Observatory. He received a Bachelor of Physics degree from MIT in 1996, then studied at Washington University in St. Louis, Missouri, to receive a Master of Arts in Physics in 1999. He taught astronomy for 2 years at Bowling Green State University in Ohio before entering the Jesuit order in 2001. As a Jesuit brother, he received a Master of Arts in Philosophy from St. Louis University in 2006, and after a year teaching astronomy at Rockhurst University, he began work toward a PhD in physics with planetary science specialty at the University of Central Florida, which he completed in 2010. From 2011 to 2013, he studied for a Master of Theological Studies at Boston College School of Theology and Ministry, and then joined the staff of the Vatican Observatory in 2013. He became the curator of the Vatican Meteorite Collection in 2013, and to date, he has been involved in numerous research collaborations, including membership in the science teams of the Lucy and the OSIRIS-REx space probes. And he has applied his research techniques to a large number of moon rocks from the Apollo missions. Ladies and gentlemen, please welcome Brother Robert Macke.
Thank you for that wonderful introduction. Thank you all for inviting me to be here. I think I can start sharing my presentation now. Is it visible? Yeah, okay. So please forgive me if I sound a little hoarse. I'm actually recovering from COVID, and also if this talk is a little unrefined, it's because I haven't had a great amount of time to perfect it because I've been recovering from illness. So I apologize for that, but I'll do my best. And I'm going to talk to you about meteorites in the Vatican, as was mentioned. So first, I'm going to talk a little bit about the Vatican Observatory itself, what it is, its history, and its purpose. And I think some of you have already heard some of that in previous talks from Chris Corbally and others. But then I'm going to focus on the Vatican Meteorite Collection itself, how it originated, and what we have in the collection. And then some about meteorites themselves, what they are, why they're important, why it's important to study meteorites, and some of the research methods that I have applied in my research. A few interesting results. I don't want to dwell too much on the results because I want to talk also about my latest activities, in particular with OSIRIS-REx and preparation for study of the specimens that will be returned from the asteroid Bennu. So The Vatican Observatory itself has a deep history, but the modern observatory goes back to 1891. That's the institution as it exists today, has its origins with Pope Leo XIII in 1891. And it's at a time when there's an incredible amount of anti-clericalism in Europe, and the concept, the myth of the warfare of science and religion is at its height at this period of time. And so Pope Leo XIII specifically founded the observatory to be a sign to the world of the compatibility of faith and science. So in his document, the Motu Proprio Ut Mysticam that established the observatory, he spells out why we exist. That everyone might see clearly that the church and her pastors are not opposed to true and solid science, whether human or divine, but that they embrace it, encourage it, and promote it with the fullest possible dedication. And that fullest possible dedication, I really want to emphasize, this is not just that the church tolerates science, but that there is a strong support and a strong history of scientific support within the church. And the way we show the world the compatibility of faith and science is by doing good science. And we are primarily a research institution here, and we do research in all the different fields of astronomy and astrophysics. The history of church support, specifically of astronomical studies, is also quite long. It goes back at least as far as the 16th century, when Gregory XIII commissioned Christopher Clavius, who's the gentleman on the right there, to do the work for the reform of the calendar. What we today call the Gregorian calendar is the product of this effort, and this led to the founding of the Observatory of the Roman College. So there has been a papal-sponsored observatory since the 16th century, and we kind of put our origins, our historical origins, that far back, and so this begins the tradition of papal-sponsored observatories. And I'm not going to go through the whole history. There's a wonderful and deep history, but I do want to point out in particular Father Angelo Secchi, who was the director of the Observatory of the Roman College in the mid to late 19th century, so from 1848 to 1878. And this gentleman was a pioneer of astrophysics. So up until his day, people did astronomy and astrometry, that is measuring the positions and the brightnesses of stars. He was one of the first to really study stars as physical objects, and he did spectroscopy on stars. Excuse me. To try to understand what they're made of, and to classify different stars based on their spectral lines. So he created a classification system of 4 different groups that he classified about 4,000 stars by this system. And this system was later adopted by the astronomers at the Harvard Observatory and adapted, expanded to become the system that we know today. This spectral classification system that we know today has its origins in Secchi's work. He also was a solar physicist, and he set up in his observatory on the top of the Church of St. Ignatius, which you can see. I don't know if you can see my mouse, so in the picture here is the Church of St. Ignatius, and he has his observatory on the roof, but also a whole section of it, the section that's directly above the altar where St. Aloysius Gonzaga is buried. That whole section is a terrestrial magnetism laboratory. And he set up this laboratory to study the connection between the Earth's magnetic field and solar activity. So after the Vatican Observatory itself was founded, the institution that we know today was founded, it was originally actually located in the Vatican. So telescopes were set up on the walls of the Vatican. And this lasted until around 1930, when light pollution from Rome, because of electric lights, so prior to the advent of electric lights, even the middle of a city was dark enough to do astronomy. But with the growth of electric lights, Rome became too bright and they needed a different site. At about the same time, you have the Lateran Treaty being signed between Italy and the Vatican, which Italy officially recognized the Vatican as a sovereign territory and also granted several confiscated lands back, including the grounds at Castel Gandolfo, where the papal summer residence is. And so on top of the Pontifical Palace, we built 2 telescope domes, and we moved the facility out here to Castel Gandolfo. And so the picture on the upper left there is the Pope's summer residence with 2 of our telescope domes on it. And then over time, the observatory expanded into the pontifical villas. So there's 2 more telescopes there. This houses one of these domes houses the Carte du Ciel, which was our very first telescope built in 1891, and the other one houses the Schmidt telescope, which was our workhorse telescope from the 1950s up until we stopped using Castel Gandolfo for active astronomy in the mid-1980s. And why did we stop using Castel Gandolfo? Because, well, again, lights from Rome at this point were creeping out into the countryside, and it got to the point where it's just too bright. So today, our main telescope is in Arizona on top of Mount Graham, which is about 3.5 hours drive from Tucson, Arizona. We have offices at the Stewart Observatory on the University of Arizona campus. But the telescope is on top of the mountain. And this telescope, the Vatican Advanced Technology Telescope, includes the primary mirror is the prototype, the very first spin cast mirror. That is, it was created in an oven that was spinning as the glass melted. And because it was spinning, it allowed the glass to flow into a parabolic shape. This mirror was made as a prototype to prove that the technique could work. It's only 1.8 meters in diameter, which is still a rather substantial sized mirror. But today, the Stewart Observatory Mirror Lab makes 8.4 meter mirrors. And in fact, on the same mountain, just up the hill a little bit, is the Large Binocular Telescope, which has 2 8.4 meter mirrors side by side. So our telescope, which is really a really wonderful and powerful telescope, is small in comparison to its neighbors. But it's still a 2 meter class telescope is great for a whole range of astronomy that is difficult to get time on the bigger telescopes for. Some of the projects we've historically been involved with include the Carte du Ciel program from the very founding of the observatory. It's an international collaboration of 18 international observatories that were dedicated to doing this map of the heavens. So we had a 1/18th part of the sky and basically measured the positions and mapped out all of the stars down to, I think 12th magnitude, something like that. Thousands and thousands. So we had, there was a group of nuns that did our measurements for us. The computers were this group of nuns that measured the positions of about 250,000 stars in our section of sky. We also, in our new facility in Castel Gandolfo, founded a spectroscopy laboratory. So there's a lot of spectroscopy being done in astronomy at the time. We had spectra of asteroids and planets and stars, but how do you interpret those spectra? What can you learn from them? And so it was decided to be a good idea to set up a spectroscopy laboratory to measure the spectra of rocks and pure minerals and also pure metals to try to understand better and to interpret the spectra we're seeing from these astronomical objects. And the spectroscopy laboratory led to the founding of the journal Spectrochimica Acta, which was founded at the Vatican Observatory and is still published today. It's not published by us, it's published by Elsevier Press, but it was founded here. Also in that laboratory, touching into my field, they did some of the very first spectral studies, spectroscopic studies of meteorites. Back in those days, it was a fairly destructive process, because basically what you do is you take a certain quantity of meteorite, pulverize it, and then burn it. And you would study the emission lines from the burning. So they had to destroy a fair amount of meteorite to do this. But some of the very first studies of meteorite spectra was done at the Vatican Observatory. Today, we cover a whole range of different fields. So everything from quantum gravity, string theory, and cosmology, that the really biggest scales, and like looking way deep to the origins of the solar system, the origins of the universe, and how the universe works, all the way through galaxies and stars and planetary science, all the way down to meteorites. So we cover a wide range. By the way, I have pictures here of my lab assistants. They brought their own lab coats. And this leads us to the meteorite collection and the work that I do. So the meteorite collection itself, today we boast about 1,200 specimens in the collection. And for the most part, this collection originated from the private collection of a French Marquis, Adrien Charles Marquis de Maurois, who was an avid naturalist and a collector of meteorites and minerals. He was also a devout Catholic who thought it would be a wonderful idea if there was a natural history museum in the Vatican, and so tried to inspire the founding of a natural history museum through various different ways. And one of the ways was by donating a portion of his meteorite and mineral collection to the Vatican Observatory to assist us in our research. And we received a few hundred specimens during his lifetime in several installments, but then after his death, his widow donated the remainder of the collection. So we have about 1,000 of our specimens originate from the Marquis collection. And because in those days, there was not a lot of active collecting of meteorites out in the desert, and so today most meteorites are what we call finds, where basically it might have been sitting there for thousands of years and all that stuff. People know what to look for. They go out to the right locations and they pick stuff up. Back in those days, they didn't, basically all meteorites collected in those days were observed falls. So somebody actually observes stuff fall from the sky and they go out and collect stuff afterwards. And so his collection contains a number of historically significant meteorite falls, including, for instance, Ensisheim, which I don't know if you can see behind me. There's actually a manuscript, an illustration from a manuscript that's in the Vatican Library for the fall of Ensisheim. But that fell in 1492 and was one of the first well-documented meteorite falls. L'Aigle fell in France in 1803, was documented by members of the French Academy of Sciences, in particular Jean-Baptiste Biot, and established among the scientific community the authenticity of meteorites as extraterrestrial in origin. And Weston, which fell in Connecticut in 1807, which was studied by American scientists and established for the Americas that meteorites are of extraterrestrial origin. So today the collection is very broad. We have about 1,200 specimens. It's grown slightly since the donations of the Marquis, mainly through additional donations from generous donors. And our collection contains all the different meteorite types, or at least all the major meteorite types, including lunar and Martian meteorites. We'll talk a little bit about lunar and Martians in a little bit. In addition to just having the collection for our own research, we also make the collection available for research to other scientists. So we do, that's part of my job as curator, is to loan out specimens to scientists who request them. So what's some of the kind of research we do? Well, to understand why we want to research on meteorites, let's talk a little bit about the formation of the solar system. So back when, in the early days of things, about 4.5 billion years ago, a cloud of gas and dust condensed to form our solar system. And the most of the material condensed towards the center and formed the sun. And then there was a disk that formed around that condensed to form the planets. And in the early solar system, you basically have this process of dust grains forming and coming together to form clumps, and then those clumps forming larger clumps, and somehow or other forming big enough clumps that you have what we call planetesimals eventually, and protoplanets. But also in the early solar system, things were a lot more crowded than they are today. And with interactions with Jupiter and other such things, things started to bang around a lot, which means that a lot of these early protoplanets banged into each other and broke apart. And then most of that material eventually got ejected through gravitational interactions with Jupiter and Saturn. But the remnants of that is what we call the asteroid belt, and then further out also the trans-Neptunian objects, the Kuiper belt. So asteroids are basically broken up remnants of these early protoplanets. And eventually some of these asteroids, sometimes they have Earth crossing orbits, and sometimes they fall to the Earth. And so the meteorites are basically come from these asteroids, most of them. We have a few also from Mars and the Moon, and I'll talk a little bit about that as I promised. But most of them are asteroids, and these asteroids are remnants of these processes of planetary formation in the early solar system. So they, yeah, I kind of skipped over it. So here's a picture of Chelyabinsk, which fell to the Earth in 2013 over Russia. So you have this giant fireball, which this one actually exploded over the city, and the shock wave knocked out a bunch of windows and injured lots of people. Here's a picture of meteorite Murili, which fell in Australia. And actually, this one's great because it was observed by the Desert Fireball Network. So there's a network of cameras that watch the sky, and they actually saw the fireball and were able to project its trajectory and figure out where it landed. And so they sent out crews to go out and search and to find the specimen, and they found this meteorite. There's only been a handful of meteorites that have been recovered by this method. But when we do, it's great because we have the orbit. We also have a certain amount of information from observing the fireball itself to understand, to characterize the asteroid that came in. But also we can track it back. So you track the trajectory forward to find out where it lands, but you also track it backwards to figure out the orbit that it had originally, which is wonderful. So it's great when we have something like that. And by the way, I did some research on this specific meteorite also. Most of these meteorites, there's a whole bunch of different types of meteorites out there. Some come from parent bodies that are undifferentiated. So the planetesimal that they formed in was fairly was not too big, and so wasn't strong enough to have differentiated into a dense core and a medium density mantle and a light density crust, like most planets are. So instead, everything's still mixed together. So you have iron and nickel and rock and everything else all mixed together in these undifferentiated parent bodies. And that gives us the chondrites. So there's carbonaceous chondrites such as Allende right here, ordinary chondrites like Farmington over here, and enstatite chondrites like Havidus. And those are they differ in composition, but they're very similar in origins, but probably originated in different parts of the solar nebula. Still work being done on exactly how those things connect. The term chondrite comes from the presence of chondrules, which are little silicate glassy blebs that basically formed when something about grain-sized melted and then re-solidified into a solid, basically imagine a liquid droplet that re-solidifies and then somehow got incorporated back into the parent body. There's a lot of questions as to exactly how chondrules form and the processes, not just of formation, but also incorporating into these things. So timing and sequence. A lot of studies being done on that. But we also have in carbonaceous chondrites, we can see like this white bleb here is a very refractory inclusion called a calcium aluminum rich inclusion. And this kind of stuff is among the very, very first stuff that's solidified out of the solar nebula. And so this is the stuff, when we date the origin of the solar system to 4.56 billion years, this is the stuff that gives us those dates. That basically have been preserved since the early days of the solar system. Now we also have meteorites that originate from undifferentiated parent bodies. From differentiated parent bodies that have an iron nickel core and a medium density mantle and a light density crust. So iron meteorites are from the cores of these differentiated parent bodies. The achondrites are crustal material from these bodies, and they're very similar to Earth crust material. So it's actually very difficult to identify an achondritic meteorite out in the field because it's much more similar to Earth rock than most other meteorites are. And then you also have things that form, for instance, somewhere in the core mantle boundary, like this palisite esquil here, which is a mix of iron from the core and these olivine grains, which is what composes the mantle. And so palisites are another interesting area of study because exactly what processes allow you to form this and to grow the crystals and still keep things mixed enough. It's a great mystery. Among the achondrites, we also have stuff from existing objects like Mars. So this is a specimen of Macke here, which is a piece of Mars. So at some point in the past, something knocked into the surface of Mars with enough energy to knock material off the surface, and it floated around the space until it found its way to the Earth. Macke fell in Egypt in 1911. And this particular specimen is our specimen, and it's been there's the distinction of having been handled by popes, because Pope Benedict and Pope Francis have both held it. And we also have lunar meteorites, which again, something knocks the surface of the moon with enough energy to knock material off, and it finds its way to the Earth. And there's also mesositerites. So these are mixes of iron and rock. So they're from differentiated parent bodies, but you have the iron and the rock kind of mixed together. And again, what processes give rise to that? Something worth studying. Now, what I focus on mainly are the chondrites and achondrites. That's my main area of research. And in my main area of research, I study physical properties: density, porosity, magnetic susceptibility, and thermal properties. And I'm going to focus in this talk mainly on the density and porosity. This, by the way, is a picture of my laboratory. So it's a fairly simple laboratory, and mostly the instruments are desktop, and they're quite portable, which means I can take them to other locations, which is very useful for studying other collections. Porosity, by the way, is simply the amount of empty space, the amount of pore space inside the object. And so, to find it, we basically want to measure two different volumes. We want to measure the volume, which is represented in yellow here, of the entire outer surface, like all the volume enclosed by the outer surface, which we call the bulk volume. And then also the volume just of the solid component, which we call the grain volume. And the porosity is the difference between those two. And we express it as a percentage difference. So we divide it again by the bulk volume. And also because we like to use intrinsic properties rather than extrinsic ones, we'll express this in terms of densities rather than volumes. So we can calculate the porosity as a function of the bulk and grain densities, where density is, of course, is mass divided by volume. To measure the bulk volume, Brother Guy Consolmagno back in the 1990s came up with a great way of doing this. The main issue you want to do with measuring these things is to do it in a way that's non-contaminating. So, the traditional method of measuring bulk volume and density is to submerge something in a fluid like water, but that's contaminating. That introduces contaminants, can cause rust to the meteorite. He came up with the brilliant idea of using something that acts like a fluid, but is not actually a fluid, which is glass beads. So they'll flow around and fill up all the space around the specimen without flowing inside and without contaminating it. So you place your specimen in a cup of known volume, you fill that cup with beads, you weigh it, and some calculations to calculate the volume of your specimen. Now that's great, except that those beads get everywhere. When I first started doing research in this field, I was doing the beads and it got everywhere. So I was very happy when we shifted to 3D laser scanning around 2015. And this is a process where you simply scan the outside of the meteorite and create a model of the specimen in the computer and calculate the volume from the model. So no beads, it's great. And the reason why we switched, aside from the fact that it's a good idea, is that I was doing some research on moon rocks, and they had some concerns about the beads, and they made us use alumina beads instead of glass. And the alumina beads had this static electricity problem where they would just, they'd literally be jumping out of the cup. And so there's no way to get any good data. And then one of the guys said, "Oh, we've got this laser lying around here we haven't used. Yeah, let's give that a try." I'm like, "Yeah, let's do that." And I never looked back since then. It has so many advantages. First off, no beads. But like I said, those beads get everywhere. I used to go to lunch and I'd bite into a sandwich and I'd bite into several beads as I was biting my sandwich. Not fun. It's also something that's contactless. The laser doesn't come in physical contact with the specimen. So here's a specimen of orgeat, which is a CI carbonaceous contrast. It's extremely friable. You would not want to insert it in the beads because you run the risk of basically just disintegrating the specimen. But you're able to put it on the laser and measure it by the laser. It's also, the laser is much more precise than the beads, gives a greater range of specimen sizes, and we get a 3D computer model in the end, which we can do fun things with, including print out a version of it, which if you want to show meteorite, some of the interesting surface features on a meteorite, that's a nice way to do it. So with regard to the increased range of sample sizes here, I've worked with things as small as this 66 milligram specimen of Almahata and things as large as this almost 500 kilogram specimen of Fukang. And with the same laser, same device, and I was able to get really good measurements on both. Part of one of my research studies is on measuring what this has enabled me to do, I should say, is to measure the porosities, the densities and the porosities of a range of different meteorite sizes for the same meteorite event. So these are all specimens of the Košice meteorite that fell in Slovakia. And they range in size from about 0.66 grams all the way up to almost 2.5 kilograms. And I was able to measure their porosities and to find a relationship between the size and the porosity. So the the more porous portions of this object broke into smaller pieces, which is what you expect. The more porous it is, the weaker it is, and when it breaks up in the atmosphere, it's going to break up into smaller pieces. But that hadn't been measured before. So it's nice to be able to have measured it and to demonstrate it. One of the other things that we do for the grain density is ideal gas pygnometry. Ideal gas pygnometry uses the ideal gas law, which is, well, we actually use Boyle's law, ideal gas law at constant temperature, which means that the pressure times the volume of a gas, if you keep the temperatures the same, the pressure times volume also stays the same. And so you take your specimen, you insert it into a chamber of known volume, and you pressurize a gas. So you measure that pressure times volume, and then you open up the chamber, you expand it into a larger volume, and measure. As you expand to a larger volume, the pressure drops, measure the new pressure. And that pressure times volume is the same as the other one. So with a little bit of calculation, you can calculate the volume displaced by your specimen. Now, in reality, we don't use an expanding chamber. We actually use two chambers with a valve between them. So the expansion happens when you open a valve. On the left here is an ideal gas pygnometer, a commercially available one from Quantachrome. On the right is one that I built myself when I was studying theology at Boston College, because that's what you do when you study theology at Boston College. No, you don't. But I did build it while I was studying theology. And in that particular chamber there, that's actually a moon rock in the chamber, an Apollo specimen, which is why it's wrapped in aluminum foil. So there's a valve, and it expands into one of these secondary chambers for the expansion stage. And so far, I've done all this work on like 1,800 meteorites at a number of different collections. My research has involved a number of different collaborations. I'm going to skip over this quite a bit, but if you're interested in any of these, please ask me. And I've also worked with magnetic susceptibility, which I'm not going to talk about, and measuring thermal properties is one of the big things I'm working on today, working with Father Sayo Peel at Boston College, who has this physical properties measurement system here that is great for measuring heat capacity and thermal conductivity and things like that. Real quick, I'm going over time than what I expected to go, but I'm just going to go real quick over this. Some of the things that we've recently uncovered. So one of the earliest results of my research was finding that using grain density and magnetic susceptibility together was a neat way of distinguishing the three different types of ordinary chondrites that are notable by their difference in metal content, HL and LL meteorites. If you use grain density and magnetic susceptibility together, these things distinguish themselves quite easily on the plot into three different groups. That was work we published in 2006. With my work on Apollo moon rocks, one of the things that my colleague Walter Kiefer and I uncovered is we adjusted some of the interpretations of data coming from the Grail gravity observer, lunar gravity observer. So it measures gravity anomalies on the surface of the moon and uses that to understand and interpret the thickness of the lunar crust in different parts. And by adjusting the densities of the lunar soils based on the moon rock work that we had, we're able then to readjust the inferred thickness of the crust of the Orientale Basin. And we adjusted it by 25%. So it's 25% thicker than previous estimates. With our thermal properties, one of the interesting things we found is that with certain types of carbonaceous chondrites, the CM carbonaceous chondrites, we observe a negative thermal expansion, which means that in a certain temperature range around 235 Kelvin, as the temperature increases, instead of the rock expanding, which you normally get, it actually contracts a little bit. And we hypothesized that this would lead to a certain amount of instability and fragility, as if its diurnal temperature cycle covers that temperature range, it probably would accelerate breaking up specimens. And this is actually relevant to the work on OSIRIS-REx, because we expect that the asteroid Bennu is predominantly CM or similar to CM carbonaceous chondrites. So it probably has undergone similar processes. Speaking of OSIRIS-REx, finally we get to the good stuff. This is a sample return mission that's going to the asteroid Bennu. And it will return its cargo to the Earth on September 24th of this year. So, the clock is ticking. It's going to be on its way. And a sample return mission is very expensive and it provides a limited yield of material, but it gives us something that we don't have with meteorites, which is context. We know exactly where this material came from. We have we have characterized the asteroid as best we can, and this gives us a lot more material to work with, a lot more information in this contextual information. So what we think we know about asteroid Bennu is it's analogous to CM chondrites. We think there's more than one type of material on the surface, just from the photographs and the spectra we have. I mean, you can see in this photograph, you see dark and light material, and we think those are actually different kinds of material. And we think it's very porous, both in its overall structure, but also inside the rocks themselves. We think the rocks themselves can be up to 50% porous, which is unbelievable. And we'll be able to understand that better by actually studying the specimens once they return to the Earth. It'll help us to quickly distinguish diverse lithologies. So if they're different types of rocks, they'll probably have different densities and porosities. It'll also, we can constrain some of these models of the interior structure and the amount of overall porosity of the asteroid by better studying the densities and porosities of the rocks themselves. So here's some wonderful pictures. The upper left is the tag SEM head, the sample and acquisition module that actually touched down on the surface of Bennu and shot up a bit of nitrogen that knocked material into the collection chamber. And we think we have at least a few hundred grams of material at this point. We won't know for certain until it arrives. But the tag SEM head, as you can see in the lower pictures, got stored in this sample return capsule. So it got sealed in real nice, and it's been sealed in for the majority of the journey. And when it returns to the Earth, this capsule is going to come to the Earth. The spacecraft itself will actually continue, and we have an extended mission for it to visit, among other things, the asteroid Apophis. But it won't collect any further samples because we've already used the collection device. And in my work, I was asked, when they were setting up the sample analysis plan, they realized they wanted density and porosity, and then they said, okay, who do we want to work on this? And they asked me to do at least the grain density work and the pygnometry, because they knew that I had a certain expertise in the field. And so I've been in the process of custom designing a new pygnometer. This is by the same principles as the other pygnometers. So the thing out front here is the sample chamber. So the specimen will go in here, and that will that is what gets initially pressurized. And then this part here in the middle, this semicircular part, is the expansion chambers. So a valve will open to expand gas into that for the second part of the measurement. And all of the plumbing and stuff goes in a box. And this is going to go in a glove box in the clean room. And so this part on this side will be inside the glove box, and then the plumbing and material will all go on the outside of the glove box. And there's a porthole, a 4-inch porthole in the box that it'll pass through. It'll get mounted on and then pass through. This is some stuff from a test run, an exercise we did in March using a prototype of the pygnometer, which is done with 3D printed materials. The final one will all be done with curation compliant materials, stainless steel and aluminum. But here you can see the sample handlers practicing using the device. This is not the exact same circumstances that it will be done in the real thing, but this is their first exposure to the device and how it works, and so they're getting some practice using it. And by the way, in the lower right there, that's me with my wonderful beard mask on. That's great. And then, oops, here's a little, the next step in things is actually producing the final version of this thing, which we have been working on very hard, and it'll have to get super cleaned and everything, and it'll be assembled in the clean room. But here's a video of its assembly that I put together. And I mostly put this together just so that I was sure I knew all of the parts that had to go into the thing. But it's also a wonderful description. So the 4 bits that were sticking up there were the electronic valves that open chambers. The long tube on the left there is the pressure transducer that measures the pressure. This is the whole mounting system that it goes on, and that is the expansion chamber. You can see it's actually 3 chambers on the inside, so we can select the size of chamber we want, and that's the sample chamber. And everything will have to get wired up to connector. And the outer portion is actually going to be wrapped in a Teflon bag to prevent any contamination. And then there it is being inserted into the glove box. And there's this little support leg that's going to go in. A little sample tray that'll assist the operations. And this little cup is, the sample is going to fit in a little cup. And that's the lid that'll close over it to seal it up. And that's the whole thing. And on the left here is a picture of the actual clean room, and the glove box that my device is going to be installed in is the one in the back. The one in the front here is the one that they're actually going to be doing the operations on the specimens, the initial operations on the specimens, picking them out, studying them, and all that stuff will be done in there. And then when they're ready to do picnometry, they'll get transferred to the glove box in the back. And I'm going to look like these people on the right here. So this is Nicole Lunning, who is the one of the curation specialists, and Dante Loretta, who's the PI for the mission. But you can't really tell who's who, and I'm going to look exactly like them when it's my turn. So, all right, that's all that I have. So I look forward to what's coming up next. So thank you very much for your time. And I think I'm going to stop sharing. There.
Thank you so much, Brother Bob. That was a very informative and comprehensive lecture. Actually, I had a hard time following everything, but I tried my best. We have some.
I think I crammed too much in there. I'm sorry.
It's okay. But there are some. I would like to ask first the basic questions that were being asked here. We do have students who are also watching the presentation, and there are two related general questions here, like basic questions like, well, what is the difference between a meteoroid, a meteor, and a meteorite? That's the first question.
Okay.
Yeah.
Yeah, it's mostly one of those weird little semantic things. So a meteorite meteorite refers to something that has landed on the Earth and can be collected. So ite, the suffix ite refers generally to a rock. And so meteorite is a rock that can be collected. A meteor is when you look up in the sky and you see a little flash of light in the sky. So like a shooting star, that is a meteor. And a meteoroid is an object that is heading to the Earth, but is not yet here.
Yeah.
So each of those words sort of has a somewhat different origin, which is why we have different, even though they're related, we make those distinctions because they came about. And meteor, by the way, meteo just refers to the sky. So which is why you have meteorology is the study of weather, because weather is a phenomenon of the sky. A meteorite is a rock that has fallen from the sky.
Thank you for the very nice explanation about the terminologies. A related question, I guess this is for those who are observing meteors. So what is the difference between a meteor, a fireball, and a bolide? You mentioned that in your presentation as well.
Yeah. Since I don't generally work directly in the field of fireballs and meteors, I'm not going to make a specific distinction. But basically, bolides and fireballs are the same thing, in my understanding. And meteors generally refer to the smaller objects that just kind of create a little little shooting star. So they're basically grain-sized objects that enter the atmosphere and burn up, whereas the bolides and the fireballs are bigger objects that really light up and have the potential to have material survive to hit the ground and to be collected as meteorites.
Good. Thank you. So you pronounce it bolides.
Yeah, I do.
And how can this is a play of words. So how can you? I guess if you see what is supposed to be meteorites, how can you tell it a true meteorite from a meteor wrong?
There are a few tells. Ultimately, if you want to be sure, you take it to a laboratory and you study its isotopes, because there will be some distinct differences between for instance, an oxygen isotopes between something from the Earth, something from the solar system. So different types of meteorites have different oxygen isotopes. That's another way of helping to classify them as well. But there are a few things to look for. One of them simply is density, because meteorites tend to have a lot more iron in them than Earth rocks. They tend to be denser. And so, a rock that's much denser, much heavier than it should be for its size is more likely to be a meteorite. Oftentimes, especially if you find a fresh meteorite, it'll be covered with a thin surface of a dark material. This is called a fusion crust. That is something that forms on the surface as it is coming through the atmosphere at hypervelocities. So the friction with the atmosphere basically melts the outer surface a little bit, and then as it resolidifies as this smooth, dark crust that's very thin, less than 1 millimeter thick, and it's very different from the inside of the rock. It's not a process that really happens to form terrestrial rocks. So if you have a fusion crust, there's not much in the way of terrestrial processes that would form that. So that's another strong sign that you have a meteorite.
Thank you.
And there are a bunch of other things to look for, but I'll just leave it at that for now.
Well, is there
are resources
any,
to look for if you want to learn more.
Oh, so you really need to be an expert before you can, or at least some.
You don't need to be an expert.
Yeah.
I think it'd take longer. I could spend the rest of the evening answering that one question. So I'll just refer that to online resources that'll help.
Well, the next question is related to that, because when I visited some of for example, here in the Philippines, some of the malls are actually selling what they call meteorites, but they are actually what they call we term as tektites. And this is very common here in the Philippines. So are tektites considered meteorites? These are the dark stones that they are selling. Yeah.
They're not. They are material that have they're terrestrial material, but they've been ejected, and so they'll often have a fusion crust, but they're not considered meteorites. And some of them, in fact, are not even so. Some of them are secondary from, for instance, you have a meteorite impact with enough energy to knock material up. And material will go up and then re-enter the atmosphere. So you have Earth rock that has re-entered the atmosphere. But you also have stuff of volcanic origin that gets kicked out by volcanoes, and then goes with enough energy to go up. So you even have different processes that produce tektites. But I'm no expert in tektites, so I have to say that as well. I know people who study them much more than I have.
Thank you. You mentioned that some of the meteors originated from Mars or the moon. So the question is, how would you know the meteorite came from Mars, the moon, asteroids, or from other solar system residue?
It really helps if you have something to compare it to. So with the Mars and the Moon stuff, we've sent probes to, well, with the Moon, it's easy because we've actually gone to the Moon, picked up rocks, and so we have something directly to compare with. With the Mars stuff, we don't have any sample return stuff from Mars, but we have sent probes to Mars, and we have measured the composition of the rocks as best we can. We have measured the composition of the atmosphere. But you also have a number of different other lines of evidence that kind of indicate. One of the things is the Mars rocks are much younger than, for instance, the other meteorites. So asteroidal meteorites, the vast majority of meteorites, are all 4.5 billion years old. They all basically have their origin at the origin of the solar system. But the Mars rocks are maybe 1 billion years younger or more, which means they had to have formed in an object that was still geologically active much later in the history of the solar system. So it was still making new rock. And so it had to have been something about the size of Mars. And you have these other lines of evidence geologically that kind of point to Mars. And then you also have isotopic evidence, and you have ultimately some of these Martian meteorites have gases that were trapped from bubbles that were formed during the ejection event. And they preserved inside them pieces of the Martian atmosphere. And because we have measured the Martian atmosphere from the Mars probes, Viking and others, then we have something to directly compare that with, and they match perfectly.
Yeah, Brother Bob, I remember there was this meteorite that they discovered in the North Pole or in the Arctic, and it was determined to be of Mars origin. That's how it was determined. You were mentioning the chemical composition.
Yeah, so a number of Martian meteorites have been discovered in Antarctica and other places. So every year there's a mission to Antarctica to collect meteorites. Antarctica, by the way, is a desert. It's you don't think of it as a desert because it's covered in ice, but it's solid ice. It never rains there. You don't have liquid water in Antarctica, which means it preserves meteorites incredibly well. And over time, you get this solid blue ice, and the only thing on it is these rocks. Where do these rocks come from? So every year there's missions to Antarctica to pick up meteorites. And so they've collected thousands and thousands of meteorites from there. And many of them are Martian. So it's a wonderful source for material to study.
Yeah.
I forget
There's
you had another part of the question there, but
yeah. Well, but the other one is going back to the question about how to determine whether it's a meteorite or not. The question is, are all magnetic rocks of meteorite are they meteorites? That's one of the questions.
There are a number of rocks, of terrestrial rocks, that are also magnetic. So, for instance, there's historically, a magnet. The way you would get a magnet is you actually find a magnetic rock, what was called a lodestone. So, like we didn't have neodymium magnets. You just go out to the store initially. You had to actually find a rock that was magnetic if you wanted to find a magnet.
Yeah, thank you. Now regarding other ways of studying meteorites, the question here is: cometary and asteroid spectroscopy relevant to meteorite studies?
Yes,
Yeah.
The spectroscopy is quite relevant to meteorite studies. In comparing the spectra of meteorites and the spectra of asteroids in particular, to try to find the connection to say, okay, we have different special classifications of asteroids. We have S class and Q class and M class, and it's basically, you know, their spectra have different profiles. And one of the things that there's a lot of attempt to do is to connect this type of asteroid profile relates to this kind of meteorite. So we think that these meteorites come from those kinds of asteroids. The challenge is that the stuff we have on meteorites, oftentimes the outer surfaces have been lost, and what we have is a fresh inner surface in the meteorite. Whereas what we see with the asteroid with the asteroid spectra is we see spectrum from the outer surface that has undergone millennia of space weathering. And one of the processes in the space weathering is the solar wind and other energetic interactions with the surface produce small, what we call nanophase iron. So just little tiny blebs of iron and other things that change the spectrum a little bit, turn it a little redder, make it a little different. And so even though we try to make the connection, it's not perfectly obvious because the surface of the asteroid has been changed just a little bit, enough to change the spectrum.
Thank you. There another question here. I don't know if you can answer this. It's about meteorites in the Philippines, and it says it's from Mr. Leonard Aquino, a member of the Manila Street Astronomers and a third order of preachers. And my question is, do you have any idea about the whereabouts of the Pampanga 1859? Pampanga is a province in Luzon Island. Pampanga 1859 and Calibo 1914 meteorites in the Philippines.
I do not know about those offhand. The names are not familiar, so I'm fairly certain we don't have any in our collection. So sorry about that.
Okay, thank you. And another question here from our attendees from Canada, Mr. Elian Papenberg. I heard it was now discouraged for amateurs to identify meteorites with magnets, as it could cause damage. How to find out then? From Ellen Kitchener from Ontario, Canada.
I would say it's not a major concern. One of the things is that there are researchers who try to do remnant magnetization. So basically, at some point in the past, when the parent body was more fluid, perhaps there was a magnetic field, and that magnetic field sort of got, as the rock solidified, might have gotten trapped in the rock. And so there are researchers who are trying to study that trapped magnetic field, that remnant magnetization. So if you expose the meteorite to a strong magnet, it might change that, it might alter that. So I would say if a meteorite is likely to be subject to those kinds of studies, then yeah, you don't want to hit it with a magnet. Now the question is, how many meteorites will be studied in that way? You know, I would say there's certain special kinds of meteorites that would be, but you know, if you're just collecting one for yourself or something like that, and it's not likely to end up in a research collection, I wouldn't worry about it.
Thank you. And this one is maybe from another one of our students. What is the best way to start a meteorite collection out of a shoestring budget? Any recommendations?
That is a good question.
And the follow-up question is this: why are meteorites so expensive?
one of the reasons meteorites are expensive is because meteorites are expensive. So there was a program on TV a couple decades ago called Meteorite Men. And so you have these guys go out in the field and they find meteorites. And every time they picked up a meteorite, there was a little cha-ching and a little price tag showed up on the screen. And since that time, the price of meteorites has skyrocketed because you have a lot of people who suddenly saw meteorites as a financial investment. And so really kind of, they drove up the price several orders of magnitude. Well, not probably an order of magnitude, a lot anyway. Yeah, meteorites are expensive because meteorites are expensive.
Well, here's another question about terminologies. What are meteor showers? Why are they called meteor showers?
So every so often, so as the Earth orbits the sun, it passes through the remains of a cometary trail. So as the comet passed by, and so there's an increased amount of dust from the comet in that section of the Earth's orbit. And so as the Earth goes through that amount of dust, it picks up a whole bunch of it, and the stuff falls to the Earth in meteors. And so you see a whole bunch of meteors kind of all within a day or two together. And that's a meteor shower. And these are all dust-sized particles that are remnants of this comet. There are a number of different meteor showers throughout the year because we pass through the trail, not the tail, of a number of different comets. So the Perseids and Leonids and all that, and all of those are passing through the path of a comet.
Thank you, Brother Bob. And again, another question here from the attendees. What are the chances of a person getting killed by a meteorite falling from the sky? I've heard of some near misses, but have you heard of somebody getting killed from a meteorite falling from the sky?
The only case that I am aware of is somebody who was not hit directly, but was hit, basically it fell through their roof and bounced off the thing before it hit them, which is good because they got a pretty bad bruise rather than, seriously injured or killed. The most injuries actually are from the Chelyabinsk event, which was not anyone directly getting hit at all, but it was the shock wave from the explosion knocking out the glass windows. And of course, everyone had seen this fireball and went to their windows to look and see, oh, what is that? And so they're all standing by their windows as the window, and so they got a lot of injury from the broken glass, but not from anyone actually getting hit.
Thank you. So it's very, very rare. Maybe it's you have more chances of getting hit by lightning, right?
Oh, much more, yes. Because there have been a number of documented cases of people being hit by lightning, including, I think, somebody who was hit twice.
And if I may ask, this is a question from one of our Philippine attendees, from Thomas Encarnacion. How would a discovery of evidence of extraterrestrial life, may it be intelligent or not, from meteorites fit into the Catholic faith?
We don't have any specific policy or anything on that. When it comes to extraterrestrial life, the first and most important thing is to learn about it. So, we don't know whether there is life out there or not. I expect it's a big universe. It's likely that somewhere out there is. It's unlikely that we're going to find any in the solar system, but I could be wrong. But it is a big universe out there, so but yeah, the Catholic Church does not have any specific policy or theology or whatever about extraterrestrial life.
Yeah, thank you. I remember there's a book by Brother Guy Consolmagno, a book or article. He said, "Would you baptize an extraterrestrial?" Maybe we can ask Brother Guy. He will be our next speaker next month. Yeah. I guess I went through all the questions. Do we have any questions from our panelists for Brother Bob?
Actually, I do, Jet.
Yeah. Okay.
Yeah, but before I ask my question to Brother Bob, I just wanted to add something to the terminology that he explained at the beginning of the Q&A about meteoroids, and meteorites. Now, meteorology, as Brother Bob has mentioned, is the study of the weather. And the study of meteorites, the science of the study of meteorites is meteoritics.
Yes.
So Brother Bob is a meteoriticist, not a meteorologist. Just wanted to make that
Exactly.
because some people might ask you about the weather. So just wanted to clarify that. So my question is, we all heard about the DART mission of NASA, and it was able to demonstrate that it could nudge an asteroid, a sizable asteroid, a little bit, try to deflect it. Now, my question is, based on your study of the density and porosity of meteorites, would it make more sense not to try and hit an incoming asteroid, because it could end up, breaking up in a million pieces, and just leave it intact? So we're dealing with just one single object. Which poses more threat to us, do you think?
Well, you definitely want to leave the object intact and try to move it. Breaking something up without changing the orbit just, doesn't. You still have the same amount of mass coming to the Earth. So if it's a matter of deflecting something, you actually want to try to move it. One of my research programs, one of my collaborations, involves George Flynn, Dan Durda, and Melissa Strait, who do hypervelocity impact studies, and particularly measuring a recoil parameter. So this is done at the NASA Ames Vertical Gun Range, and you have a meteorite hanging on a string, and you hit it with a projectile, a plug that's going at very high velocities, 10 kilometers a second, something like that. And it hits it, and you measure the deflection of the meteorite. And the goal of this is to make a connection between that and the porosity. It's one of the goals, at least. Is this recoil parameter is actually dependent on the porosity of the rock. And so understanding that and understanding the relationship between how much deflection you get versus the porosity. And it's a nonlinear and non-trivial thing, because what happens is, as you impact, you actually eject a bunch of stuff out the other end. And that ejection of stuff actually creates a little jet that actually pushes things a little more than, and so, I think higher porosity stuff actually sometimes, depending on the structure, produces a larger jet. And so you actually can sometimes get a greater recoil with a more porous object. But if you don't have a jet, if you don't have any that kind of reaction, then what happens is that the porosity with the more porous object will tend to absorb the plug, will absorb the projectile, and give you a reduced amount of overall response. So yeah, it's all this stuff is non-trivial, but porosity comes into play very importantly in it.
Yeah. Yes.
I think Brother Bob, my concern is if it's a known asteroid, known object that's coming in, and you have studied it in the past, then you have more or less an idea of its porosity and density.
Yeah.
But if it's a newly discovered object, you don't really have time to study it in detail, and that's the big unknown. You don't know the physical characteristics of that object, and if it's coming in within a few days or weeks, then there's not enough time to study it.
Yeah. If you don't have enough time to study it, you probably also don't have enough time to do anything. So that's one of the problems. When it comes to deflecting something that's on an Earth trajectory, the thing you want most is time. The more time you have, the less you have to do to deflect the orbit. Because a small deflection 100 years in advance is much more valuable than trying to deflect something, 20 degrees in its orbit 2 weeks out. So it's much easier to, if you have a lot of time, it's much easier. You can plan more and a less effort required to actually have an effect.
Thank you, Brother Bob. And Imelda just wanted to show you something.
Oh yeah, Brother Bob, you are right with the price of meteorites going up tremendously. 5 years ago, for our 25th wedding anniversary, Edwin and I decided to change our wedding band to a Gibeon, Gibeon meteorite band. And so we were excited about it, except a few years ago, Edwin's ring fell off his finger because it was loose, and he did not know where it is. So I had to search for a replacement, and now it's thousands of dollars for just one ring.
Wow. Oh,
Yeah.
For Gibeon. Yeah. And so I was amazed at how the price jumped from a few $100s to several. I mean, there were some that I saw that were $2,000 for one.
Wow.
Thank you.
Thanks.
I have another question here from Leonard Aquino. I guess because we noticed you seem and the group are very excited about asteroid Bennu. So what are your expectations for asteroid Bennu?
Well, I have a lot of hope for it. One of the things is it's going to return to the Earth much more material than all of the other asteroid return missions combined. And we hope to have a number of intact stones. Now that'll depend a lot on whether or not these stones are strong enough to survive all the G-forces and everything involved. That's where things really get exciting for me, is because all of the intact stones are going to go through my machine, at least as many of them as we can reasonably do. That's one of the reasons why we're doing it all in the glove box, is so that they can go through my machine and still maintain what we call curation pristinity, so that they're still in the same basic state as they were in before they went through the machine. And I'm hoping that what I hope is that these specimens show a wide variety of different densities and porosities, which will really justify a lot of the extra work that we're going into with all this. But it will also show just how diverse a single asteroid can be, because it would really demonstrate that it's a lot of different stuff altogether. Well, there may be one thing that's dominant, there may be a whole bunch of other stuff mixed in, other different types of meteorites. We've already seen that with the Alma-Hattasida event in Sudan, that there's a number of different meteorite lithologies from Alma-Hattasida, but it's not something we've seen a lot of, and it'd be nice to actually have the specific asteroid studied as well as the specimens. So yeah, that's what I look forward to.
Thank you. Any other questions from our panelists?
One.
Yeah. Yes.
Hi,
Peter, yeah.
brother. Hi, brother Bob. Thank you for the lecture. It was very informative. And I have a question. Yeah. So, when you retrieve a meteorite, is it possible from our technology to determine which group of asteroid it originated from, such as if it came from the main asteroid belt or elsewhere?
We can generally figure out a general type of asteroid that it came from, but just finding something out there in the field somewhere does not give you its orbital origins, which is why it's also very valuable to have these fireball networks that actually observe the stuff entering. And you can project you can project the trajectory backwards to determine an orbit. So we have, I think, 2 to 3 dozen specimens right now that have the orbits plotted out of thousands and thousands of meteorites.
Okay, so last question. Yeah, so I understand that the Apollo asteroids are the ones that hit us head on or on certain times of the year. Now, are the Apollo asteroids mostly made based on what most of the meteorites have been collected so far?
I'm sorry, I've not heard that term, Apollo asteroids. I've not heard that term.
Because we have like near Earth asteroids.
So yeah, we have near Earth
normally
asteroids, yes.
yeah, so basically there are like 3 of them, and the Apollo asteroids are the ones that intersect the Earth's orbit. So I was wondering what are the most type of meteorites mostly hit us when based on your collection?
The stuff in our collections is most abundant is the ordinary chondrites. So this is when you take the overall what's out there, particularly considering the thousands of meteorites from Antarctica, which preserve, I think, the best record of what's fallen to the Earth. It's something like 70 or 80% carbonaceous or ordinary chondrites. So it's a vast majority is ordinary chondrites.
Thank you very much. Thank you.
I forgot to ask another question. This is again from our attendees. I guess this has something to do with the Vatican Observatory, Brother Bob. I guess they noticed that both you and Brother Guy are Jesuits, and the question is, how is the Vatican Observatory administered? Is it confined to a particular order? Or
so
yeah.
it was decided in the early part of the 20th century that it would be one religious order that would run the observatory, and that would be Jesuits. When it was originally founded, there were many different people of different orders. So the first director of the observatory was a Barnabite priest, but it was decided, and it's something that works very well administratively, because we have directly upstairs from me is our Jesuit residence. So all of us live together. So we live with a common order, a common way of life, with a religious superior who can be superior of all of us. And also because of the Jesuit special fourth vow with regard to mission, the Pope can easily staff the Vatican Observatory by asking the Jesuit general to supply more men. So, yeah.
Thank you. Thank you so much for sharing that, Brother Bob. And thank you so much for your patience in answering all of these questions. And of course, for that wonderful lecture.
That,
So yeah,
a quick question for Father
yeah, okay.
Bob. Brother Bob, isn't it only, I don't know of any other orders in the Catholic Church that has scientists other than Jesuits, right? Or
There are a number, perhaps not with as much of a tradition, but certainly, the Dominicans. The person who discovered the asteroid series, the very first asteroid, was a Theatine priest. Giuseppe Piazzi was a Theatine. And then the person who did who basically came up with the Big Bang Theory was a diocesan priest. Georges Lemaitre was a priest of the Diocese of Leuven in Belgium. While perhaps there are more scientists who are Jesuits than of other orders, we're not the only ones. And in fact, there are two diocesan priests who are strongly affiliated with the Vatican Observatory, who work with us directly. Don Alessandro Mizzolo, who studies galaxy clusters, and Don Matteo Gallaverni, who does cosmology and string theory. So more diocesan priests involved as well.
Thank you. Anything else from the panelists? Thank you. So thank you so much again, Brother Bob, and for kindly as a small token of appreciation, kindly allow me to present to you our ALP certificate of appreciation for your wonderful talk. And this reads as follows. This certificate is presented to Brother Robert J. Macke, SJ, for his invaluable insights, experiences, and expertise shared with the participants of the online talk entitled Meteorites in the Vatican, held as part of the ALP Astronomy Expert Speaker Series of 2023, given this 24th day of June 2023, signed by Mr. James Kevin T., President, and Dr. Jose Francisco Aguilar, Vice President. And before we end, Brother Macke, maybe we can have a group picture.
Okay.
Okay. Okay, look front. 1, 2, 3. One more. 1, 2, 3.
Can you do the gallery mode? Yeah, that's fine.
Okay.
Yeah.
Thank
I think I
you.
was looking up somewhere else. Sorry.
Okay, one more. 1, 2, 3. 1, 2, 3. Okay, got it. Thank you.
Okay, thank you.
Thank you, Brother Bob.
Thank you very much, Brother Bob.
Thank
Brother
you, Brother
Thank
Bob,
you.
for
Grazie. And Father
There you go.
Chris was right. He spoke highly of you, and you are a wonderful speaker.
Well, thank you. Thank you.
Yeah. Thank you, Brother Bob.
And thank you all for having me.
Thank you, Brother.
Oh, Jet,
And-
maybe you can announce the next speaker.
Yeah, are the slides okay? I'm having a problem with my interface here. Are we good?
Yes.
Okay.
Okay, but before we conclude today's webinar, I would like to thank all our attendees for joining us. And we will be sending your certificate of attendance for today's webinar by email to all registrants who were able to join us today. And as mentioned earlier, this is the 15th webinar in our ALP Astronomy Expert Speaker Series since we started last year. Our first speaker was the late Dr. J. Pasakoff on April 23, 2022. Our other esteemed speakers since then were Mr. Zolt Livey, Mr. Joe Rayo, Mr. Fred Espenac, Mr. Robert Reeves, Mr. Ken Crawford, Mr. Dave Eicher, Professor Matthew Barlow, Mr. Scott Roberts, of course, Father Christopher Corbali, Mr. David Levy, Mr. J. Kelly Beatty, Imelda Johnson and Edwin Aguirre, Dr. Daniel Green, Dr. Deborah Elme Green, and of course, for today, Brother Robert Macke. We are so grateful for all our webinar speakers. who very generously gave their precious time to share their knowledge and expertise to the world as amateur astronomical community. We can never thank you enough. So these are all the previous presenters in this slide.
Jet,
And
like you
yes,
had, Dr.
Heidi.
Heidi Hamel.
yeah,
Yes.
Dr. Heidi Hamel. I forgot to include Dr. Heidi Hamel.
Also, Elme Green, Dr. Deborah Elme.
Yeah, Deborah Elmegrin. Yeah, I think it's there. And for those who actually missed our previous ALP Astronomical Expert Speaker Series, you can visit our ALP official YouTube channel. Just search Astronomical League of the Philippines in YouTube. And the recordings of all the previous Astronomy Expert Speaker Series webinars can be viewed there at your leisure. Thank you. And the next online talk for our Astronomy Expert Speaker Series will be on July 22. That is a Saturday, 8:30 Philippine Standard Time or 8:30 a.m. EDT, by none other than Brother Guy Consolmagno. He is also called the Pope's Astronomer. I saw it in YouTube, and the director of the Vatican Observatory. Brother Consolmagno will discuss another very interesting topic entitled Vesta and the Chaotic Formation of Planets. We will be posting the registration link for this free webinar at the webpage of the Astronomical League of the Philippines. Again, this is a free webinar, just like all our past webinars. So please register once we post the link at our ALP webpage and our social media Facebook page. See you next month.